So what are we starting with this week?
A wee review.
A wee review?
A wee review?
Yeah.
A 5-star wee review. So it says, actually, this podcast is really good. That's
actually.
it. That's the wee review.
Actually.
That's it. That's the wee review. Shall we start the show?
Go on,
That was quite a wee review.
Hello and welcome to SCI GUYS, the show where we talk about the crazy, weird, and wonderful stories from the science world. I'm Corey, and as always, I'm joined by my co-hosts, Jamp and Luke Cutforth, and this
Hello.
week's special guest, NoahFinnce.
Hello
Hi.
there.
What?
This week, we will be, and we won't be.
Oh,
Ooh, getting
no.
philosophical this week,
Ooh,
are we?
Hamlet.
We're getting... I'm surprised you know that.
I didn't finish it, but I wrote an essay on it.
Very good. Well, this week we're talking about many worlds theory. It was voted on by our patrons, our lovely patrons, over at patreon.com/SCI GUYS. Yes. If you're listening to this today,
Patrons.
you may have also listened to our patron live stream, which was a lot of fun, wasn't it? We had a good time.
That was really long and really great.
It was a great time
So
speaking
fun.
to all of you guys.
Yeah.
It definitely
I'm not
happened.
doing this again. I'm not doing this. We record these episodes before they go out. Get over it. I'm not living your lie.
I have no idea what Luke's talking about, but we did have a good time today.
It was really fun, to be fair.
No, but if you want to be a patron and have a good time like we had earlier on today, you can join us at patreon.com/SCI GUYS. You get lots of cool stuff. You get bonus episodes. You get to vote on things like this episode. You get to suggest episode topics. Like this episode topic was actually suggested by one of our patrons. There's loads of other cool
Well
stuff,
done.
like early access to, new shows,
Yeah.
bonus bits. And also you get to help us make all these new shows that we're making, like the new SCI GUYS, short ones, the little SCI GUYS Y episodes.
It's really too much for giving.
Little secrets as well.
Little secrets.
You whisper little secrets to the patrons.
Yes, we do. Little tiny secrets. In the
Little tiny
patron-only
little
Discord,
ones.
we whisper tiny little secrets.
We shout
Don't
big
tell
secrets
anyone.
over there. Big secrets. Patreon.com/SCI GUYS.
Shall we get into talking about quantum mechanics then?
Oh, God.
Oh, yeah. Just a typical Sunday.
Noah, I'd like to start by asking you how whether you know anything about quantum mechanics, because I think it'd be so exciting if you don't and at the end you do.
I stopped studying physics at the age of 13.
What? That's not even legal.
It is. For some reason at my school at GCSE, you didn't have to take all the sciences, so I took biology and chemistry because I'm bad at maths and bad at physics, so I know nothing.
Do you know what an electron is?
An electron is a little. It's a. Oh God.
Little.
It's
it's not chargy
electrical. Boy. It's a little thing. It's
Close enough. Very good. That's all you.
We'll take it. You are a millionaire.
Yes.
That is where the bar is, people. It's
I don't know anything.
cool. Well, that's fine. You'll know something very, very soon. So we was this as we said. Gonna keep on going. As we said, this is a many worlds theory episode. The multiverse was what was suggested. So first, before we get into this, we need to talk about quantum mechanics, because that's kind of where this theory comes from. It's the many worlds interpretation of quantum mechanics. So we need to talk a little bit about quantum systems and how they work. Does anyone know about how quantum systems work, Luke?
Not pointing at anybody.
What do you mean how quantum systems work? I mean, I guess what you might be alluding to there is superpositional states.
Kind of. I mean, I'll go from the start to the finish. I just wanted to hint at the fact that Luke knows this about as well.
I've never felt more comfortable in a SCI GUYS episode than this one. I'm so ready.
Could you do this episode unscripted and just take over?
I could do some of it, yeah. I could do a decent chunk, but I'm not the host.
That's true, not this
I'm not
week.
the teacher. And I'd also probably say some stuff that wasn't founded, like I did on the live show when I said that left-handed people can get brain damage from changing to their right hand, which was somewhat
You don't know. Maybe they
untrue.
You got my hopes
Somewhat.
up, man. You really got my hopes up there for left-handed people.
Why
That's
do you
it.
hate them so much?
I don't know.
Awful.
But yeah.
So, quantum systems, how do they work? Well, they're not like normal stuff that we experience every day on the sort of macro scale. Macro scale, I'm going to use to mean this, kind of world that we live in, down to the sort of point of atoms. When you get smaller than that, you start getting into the sort of quantum scale. When you break atoms down into their constituent parts.
I know something smaller than an atom. It's called a quark.
Yes. It is.
There you
It's
go.
very true.
I remember
boy.
that. Yeah.
Very good. So that's it. Exactly. So quantum particles are smaller than atoms, like quarks or quarks, electrons, and neutrinos. You might have heard of some of these.
Sounds
Jimmy
like a
Neutron?
cocktail.
Oh.
Jimmy Neutrino.
That's where his name comes from.
His name comes from neutrons.
Yeah. Those are also friends with electrons and protons.
What?
They
They all hang
are.
out. They hang out together
Yeah, buddies.
quite often.
I
Wow.
mean, literally all the time.
Yeah.
they're like this.
Well, actually, they're more like
Not
more
just-
like this. You know,
The band's
this
all
is kind
together.
of this is kind of the deal. No, look, that's actually if we're talking about quantum mechanics, that's not how it works, is it?
Oh, okay. So it's here. These
You've already
guys are
said
here, and
something
then
wrong.
this guy is in every place. He's all over the place. He might be here. He might be here. He might be going a million miles an hour. He might be going 2 million miles an hour.
People listening to this will have no idea what's going on.
That's fine. They don't count.
Okay.
Please leave a review on Apple Podcasts.
Only
so
5 stars, please.
I'm so confused.
what we were just doing for anyone listening and for the people watching that are confused, because why wouldn't you be? We're alluding to the kind of model of an atom. So the model of an atom, we thought that atoms were the smallest things possible, and then we found out that atoms were made up of protons, neutrons, and electrons. And the sort of standard model for an atom used to be so sort of protons and neutrons in the nucleus, and then the electron sort of orbiting almost like a planet orbits a star. But that's not really how it works, and that's when we get into sort of quantum, the sort of quantum systems that we're going to be talking about now. Because as we said, electrons are quantum particles, so they can exist in different states, and these aren't states like solid, liquid, and gas. These are different quantum states. So that basically means this kind of probability of different kinds of measurements, sort of spin, angular momentum, and that kind of essentially what that ends up meaning is that a different sort of state means that it can be in a different place, moving at a different speed, have a different sort of spin, which are kind of qualities that quantum particles can have.
So it could be doing like whatever.
Kind of. So what that means with electrons and atoms, if we think about it this way, instead of sort of being an electron, a little sort of electron particle orbiting an atom, you've actually got an electron that can be anywhere around its atom, and we can figure out different probabilities for which position it's going to be in and what sort of spin it's going to have, or different qualities like that.
That's kind of flirty.
It's a little bit
Could
flirty.
be anywhere.
Yeah. Oh, am I in the
Mysterious.
first orbital? Am I in the second orbital? You don't know.
Might be
Why
over
don't
here.
you find out?
Am I the other side of the universe? Maybe. I'll never tell.
XOXO.
Electron. So yeah, basically when I'm saying state, I'm going to have to introduce a lot of terms, by the way. So state is the first one. When I say state, just think of that as a sort of broad description of what the quantum sort of particle is doing, where it's going, and where it is,
Yes.
essentially. Yeah? You
Yes.
happy with that?
Yes.
Good. And if you don't understand this, by the way, for anyone listening, Noah, that's fine. No,
I understood that.
no, I mean, anything coming up, if you don't understand, don't worry, because we're going to be talking about the sort of forefront of quantum mechanics to an extent. This is really, really difficult stuff. It's difficult for anyone to understand. And anyone that says, I fully understand this is lying to you. I can promise you that. I can promise you that. There are very few people on this planet that will be able to say, yep, I know 100% what I'm talking about when it comes to quantum mechanics. And you probably won't be speaking to many of them.
I don't fully understand anything, so that's okay. That's fine.
Well, maybe we can fix that. today.
Maybe I will be the first.
Wow. By the end of this
Never
episode.
say never.
You'll know more than all of us combined, which still isn't
Yes.
very much, but it's
No.
it's something. So yeah, that's what I was saying. A state is just kind of what it's doing, where it is, and where it's going. So what also makes quantum particles weird is that they're erratic, and they only really seem to exist in a particular state when they're measured. Usually with other stuff, they have their states are pretty much set, and we can watch them change, and we can pretty much tell what state something is in.
Yeah.
Whereas with quantum particles, they don't like to abide by that. They just they kind of exist when you measure them, if that makes sense. They exist in a certain state when you measure them.
Okay. I don't understand how that works, but I will say yes. I get what you're saying. I don't understand how that works, but sure.
Well, that's the thing. You don't understand how that works, and we don't really understand exactly how that works. That's what we're
Okay.
talking about today.
Yeah.
Because it is kind of a bit of a mystery how it works. So we've spoken about sort of spoken about how they can be sort of in any kind of, they can kind of be in multiple states at once, or not really have a set state until they're measured. And when they are measured, we think of them as something called point particles, which basically just means something that essentially, okay, if you think of a 3D object, a 3D shape, that's got 3 dimensions, right?
Yes.
Yeah.
I just thought of a square.
I saw your eye.
I know it's not.
So you've got 3D objects like cubes, and then if you make that a 2D object, you've got a square. Sorry. These point particles, they are a single point. Oh, a one-dimensional thing is a line. Basically. So you've got a three-dimensional object that's a cube. Bring that down to 2 dimensions. That's a square. 1 dimension is a line, and then a dimension less than that is a sort of point particle, which doesn't really have mass or area or it's just a point.
Just a single point.
Yes, just one.
You can't even see it because it's so single.
You literally cannot.
Yeah.
What with a microscope? Then how do we know it exists?
Well,
that's a very difficult question to answer.
Well,
faith.
Well, this is the thing about measurement.
Heard about our Lord, the point?
Yeah. I was like,
That's a really good thing. How do we know that they? Well, this is the thing. When we measure something with a microscope, what are we actually doing? How are we measuring it? How are we seeing
Bouncing things off of it.
Bouncing things off of it, exactly. And those things are light. We're bouncing light off of it. So we're basically hitting the thing with light, and then it's hitting back at the back of our eye, and we're seeing it. With these kind of things, they're too small really for us to see them with light. And if you were to try and see them with very high energy, sort of short wavelength light, it's got so much energy that it would change what you're viewing. So
Doesn't it create a black hole?
What create a black hole?
There are some that I can't remember. I'm completely going off memory somewhere, but there's some systems where the amount of energy you have to put in to measure them is so great that the whole system collapses.
That could be possible. I think
it creates a black hole. You'd have to put so much energy into such a confined little area that it would collapse and create a little black hole.
But then the black hole at that point would be so small that it would evaporate immediately.
Yes. Yeah.
So I mean, this is the black holes.
yeah,
don't
you
need
don't
No,
honestly. Don't
black holes
explain,
don't
'cause
need to-
it won't make sense.
Black holes need to be
me.
massive.
Yeah.
But that doesn't mean they need to be big. It just means they need, like, for a black hole to sustain itself, it needs to have. I mean, it does need to be big, but for a black hole to sustain itself, it needs to have a lot of mass. If it doesn't have very much mass, it just evaporates and stops
Like
existing.
eats itself almost.
Yeah, basically.
Yeah.
It's just kind of.
I really hope someone has clicked this video with this intent of like, I'm going to learn today about the many worlds interpretation of quantum mechanics, and then we're here.
In some universe, we're not going.
Look, we will. Look, in some universe, we've gotten to it, right? No, we will. So we will go into the sort of many worlds interpretation. But the thing is, we need to lay a pretty solid baseline before we can get into that, because there's a lot of sort of problems with the theory, and there's a lot of things that people claim that it solves, and it'll be useless if I just start telling you about it. Okay. So, as I was saying, basically, usually to measure things, we basically use light. But light these things are too small to measure with light, really. So you can kind of measure them, despite the fact that you can't see them. You can measure them based kind of on their interaction with other things sometimes, and you can measure them indirectly.
Oh, so like you can't see it, but if it has effect on something else, you can be like, oh, well, it's probably there.
Yeah.
Okay.
Essentially.
Yeah.
It's very complicated. It's kind of another episode of its own.
Yeah.
So that's kind of what we're doing at the Large Hadron Collider at CERN. Basically, we're kind of smashing particles into each other, and we can tell. I think we can tell that they're there because of kind of the effects that has.
Yeah, that makes sense.
Yeah. I mean, it's not as quite as easy as just shooting light at it and looking at it.
I think they should try that if they haven't already.
They have. Probably the
You
first.
sound
why
like
didn't we
Donald
think of that?
Trump's recognizing.
Probably the first thing that they try. I mean, okay, have a look. Can you see an electron right now?
Not that I know of.
Yeah, there you
Not
go.
currently.
Maybe later.
I'll let you know.
I don't think it works. No. So, yeah, you kind of got this understanding of how quantum particles don't really like to exist in a particular state until we measure them, and that measuring them is already kind of difficult, and different to how we'd measure things normally. Yeah?
Yes.
Okay, cool. So we're going to talk a little bit about superposition now, because we mentioned that in a bit. Do you guys know what a superposition is?
Oh, yeah.
Do I tackle this one? It's
Go
where
on, Dan.
Go for
something
it.
can potentially or does exist in two different states at any given time.
Yeah, that's a really good. So a superposition is kind of a state when something's existing in multiple quantum states at once. It doesn't just need
So
to be
like
two.
it's kind of like, is that how light works as particles and waves? Is that a superposition?
Yeah, exactly. It's when something exists in multiple states at once. Which, yeah, the sort of wave particle duality is an example of that. Another example is when we talk about Schrodinger's cat. That's an example of something existing in a superposition when it's both alive and dead at the same time. It's
Yes.
a superposition of being alive and dead.
Yes.
We'll
Could
get
it be
on-
dying as well?
Sorry?
Could it be alive, dead, and dying?
No. Look, we'll explain Schrodinger's
So
cat.
why can it? What?
Look, I'll explain Schrodinger's cat in a bit. We've got some other stuff to do before we can even think about that.
Okay.
I
Just
don't
dies instantly.
just insta death.
Lights out.
Yeah, so bear in mind that a superposition is essentially just existing in multiple states at one time without actually really fully existing in any of them. And then when you measure something, it collapses from the superposition into the state that you're measuring.
Yes.
It makes up its mind.
Collapsing isn't like a physical thing, is it?
No, it's
just
collapsing is just a word that we use when we talk about a superposition turning into something going from being in superposition to being in one sort of measured state.
okay.
So nothing is literally collapsing. We just like to use that word.
Yes.
Yeah. So we know what a superposition is. We know how quantum systems work to some extent. So we need to talk about wave functions. So a wave function is all of the sort of the total of the possible states that an object can exist in. So a wave function is just kind of everything that a particle can exist in, all of the states.
Okay.
It's a description of all of that.
Is there not like an infinite amount though?
Not necessarily.
Okay.
It's difficult to wrap your head around,
Yeah.
really. Luke, have you got a good explanation of this?
Yeah, it's a difficult one because there's so much overlap between wave function and superposition. They're
Yeah. What's
I've
the
got-
difference?
thing.
Well, that'll probably make it easier for me to understand like the difference between them.
Okay, so a superposition is just a sum of a superposition is the different states that something can exist in.
Yeah.
And it doesn't need to be all of the states. When something is in superposition, it's existing in multiple states
Okay.
at once. And the wave function is a description of all of the states.
Yes.
Okay. And this is really kind of difficult to wrap your head around, and it is complicated. So don't stress too much about it if you're finding some difficulty wrapping your head around it. So this episode is not supposed to be a complete guide to all of quantum mechanics. It's kind of just a jumping off session for you to get.
Take a while.
Yeah, it'll
Be a
take
long
quite a while.
episode, yeah.
I've got a book upstairs that is my quantum mechanics book, and it is heavy. It is a lot to get through. So we could not do that in one episode. But basically, what this is a really good jumping off point and a sort of introduction to these different sort of interpretations that we've got of quantum mechanics. So we'll get into probably more of what a wave function is later on, so you'll probably have a better understanding of that later. But let's just move on. Bear in mind that a wave function is all of the possible states, is a description of all of the possible states that a sort of quantum particle can exist in.
Yeah.
Yep. There's also another concept of entanglement, which is, you guys have heard of quantum entanglement before, I'm sure.
No.
No?
No.
Really?
Why would I have heard of this?
This is true. Why would you have heard of this?
That's true. Why would you have heard of this?
In what context? Oh, yeah, of course. Yeah. I heard of the guy.
It's used, so a lot of the time it's used as a sort of techno babble on sci-fi shows.
Oh,
If they
yeah.
want-
I don't listen to the words they're saying. I just see the outcome.
So you're like, what happens when a particle collapses into superposition? You just from superposition, you just are
I'm
the
just
outcome.
vibing. I'm not thinking about it. It just happens.
You vibe until the outcome.
Yeah,
And
I
then you're-
collapse without knowing.
Could say anything at any given moment.
People are saying all things at once
true.
until the outcome happens.
It's true.
No,
Until
so
you listen to what I'm saying. Then I say it.
So entanglement is basically just the idea of being able to infer something about one quantum system from its interaction with another quantum system.
Okay.
So I mean that's how you can actually measure. You can indirectly measure one quantum system without actually having to sort of measure it. through its entanglement with another quantum system.
Oh, so it's like when you're saying earlier, when you can't see the thing, but the fact that it's affected something else that it's interacted with shows that it's a thing.
Yeah. So in this sense, you could say, okay, let's say we've got two quantum particles that kind of sort of bump into each other, or kind of like move through each other. They're sort of they move past each other, move through each other. They are going to be affected by that sort of passing. This is not literal, by the way. This is just an easy way to understand how entanglement works. Let's say they're going to be affected by that passing. So their sort of direction is probably going to change. Their different sort of aspects of how they're moving are going to change.
Yeah.
Right. And then you can infer from one of them what has happened to the other.
Yeah.
Effectively. Yeah, because they've become entangled.
Yeah.
Because their wave functions, all of their possible states have interacted with one another and therefore changed.
Yeah.
And at that point, when something is entangled, their wave functions become entangled and are basically inseparable.
Okay.
And that gets to the point where you can take that up and up and up to the point where the entire universe is actually just one wave function.
That was a big jump.
Yeah, well,
Yes.
so, okay, if you think, so any quantum system that interacts with any other quantum system becomes entangled.
Oh, so they've all interacted with each other.
Well, okay, yeah, if you think about it, if any quantum, well, they have all interacted with each other at the very start of the universe.
Ah.
Yeah.
So if you trace it all the way back.
Big Bang and things.
Yeah.
Big Bang and things.
Yeah, I discovered how the okay.
Nobel Prize for you, sir. So basically everything is entangled. So everything shares one wave function. And that's what happens when something entangles. Their wave functions basically become, you can describe them by one wave function. But also you can look at individual systems without having to concern yourself with all of the sort of other systems, because bear in mind, sometimes the entanglement that different systems have is so sort of minute, the effect is so minute that you can basically just ignore it. It's basically negligible.
Could it also be that like once like one particle entangles with this one and then it entangles with several other, that the fact that it entangled with the first one doesn't really matter because it's already being affected by the other ones?
Maybe.
Did you understand what I said?
I'm not really. Wait, what you?
So you're starting off with one particle and it entangles with another, and you're like, oh, okay, so they're best buds now. But then it goes off and finds other friends that changes how it is because they entangle together anyway. So by the time you've got to like 5 entanglements later, the first friendship doesn't really matter
The
that
original
much.
entanglement.
Yeah, okay,
is
yeah,
kind of
fair
moot.
enough. So yeah, if you think about this in terms of the universe, right? There could be particles that were kind of bounced around towards the start of the universe, sort of quantum systems that were knocking about together, best mates back in primary school.
Yeah.
But then they're now kind of at the other side of the universe.
Yeah.
Probably not going to be having much of an effect. Yeah.
Okay.
Yeah.
So it did make sense.
It did make
Okay,
sense.
good.
Yeah. So that's entanglement. That's going to come up later as well. It's quite important to remember the entanglement. Well, the kind of idea that the wave functions become one, and you can describe the entire universe by one wave function.
Okay.
Look, you good? You look confused. Not confused, like thinking.
Well, I'm only confused because quantum entanglement has a totally different definition as well, which is entangled particles. And I'm wondering, like particles which are created where they are, where measuring one means that you know what the other one is. So I'm wondering, I've honestly never heard of entanglement being used to describe something other than that. So that's why I'm looking confused.
They sound kind of similar.
So what quantum entangled particles are two particles that are created together, and they have in some way that their states are matched and depend on each other and are connected. So if you take one particle to the other side of the universe and measure a certain property of it, instantly, supposedly, this is called spooky action at a distance, the other one, regardless of how far away it is, automatically becomes what it needs to be in order for balance to be maintained. So like imagine in a most basic level, if you measured one to be, you had ones and zero, imagine you had a binary, you measured one to be 1, then automatically, no matter how far away, instantaneously, the other one becomes 0. Faster than the speed of light. And that's why it's called spooky action at a distance, is because it seems to happen and break the laws of physics. Now, the only thing is you can't actually use that to transfer any data, so it doesn't break the law. It doesn't break the laws of physics in terms of the speed of light. But that's the only thing I've ever heard described as quantum entanglement, and that becomes very important for the sort of extended out version of the Joule slit experiment, is using entangled particles in that way, because it can be used for sort of testing the validity of your theories as to how you're sort of trying to come up with, for example, the many worlds interpretation or other interpretations of quantum mechanics.
That was very good, Luke. Yeah. So I guess what else you could take from that is that it's not just sort of particles that interact or quantum systems that interact. It's quantum systems that share sort of local space, or particles that are generated together. Those particles are going to be entangled.
Generated as in like created?
Yes.
Yeah.
Which, do we know anything about that?
Yes, but not for today.
Okay. That's fine then. I just
Stay
know that they are
tuned.
made at
Yes.
some point.
Yeah, I mean, it's a very, as I said, it's a very, very big topic, this. So for the purposes of today, we're really going to be talking about kind of sort of quantum systems that become entangled through interaction.
Okay.
And there's, as I've said, we're going to be talking about Schrodinger's cat in just a bit, which is a really, really good way to understand a lot of these topics very, very easily and much more intuitively. So stick around for that. If you're a little bit, maybe, well, I'm not sure. Stick around for that. But we need to get through the Copenhagen interpretation first, which is generally the model that most physicists today use. Of course, the many worlds interpretation is maybe
More interesting.
well, it's more interesting, I think. Yeah, but it's generally it's gotten a little more traction over the past little while, but it does have its own drawbacks, and that's the thing. None of these ideas that we've got are concrete. They're not 100%. They're not as solid as, say, other ideas in physics that we've got.
Yeah, I was going to say they're just theories.
Well, that's the thing. A theory is...
Everything is a theory, but like, are they closer to theory than...
A scientific theory isn't a... You can't say, oh, it's just a theory as a way to...
disprove something. Well, everything's a theory, really. You can't really prove anything.
A scientific theory
It's a working theory.
So a scientific theory is something that is pretty well... is pretty well sort of supported.
Okay.
A hypothesis would be something that is just...
Closer
sort
to
of-
what we would call a theory.
Yeah.
Outside of-
Generally,
okay.
people say, oh, it's a theory,
Colloquially,
meaning...
yeah.
Well, it's a hypothesis.
Yeah.
Basically, with this, the reason that I'm saying that it's not totally concrete is because there are some problems that we've got with it and some questions that we still need to answer. And there are specific issues that the Copenhagen interpretation doesn't fully cover. But then that's not to say that it's wrong. That's just to say that we could possibly just not know the answer to it yet.
Too smart for human brain.
Yes, too smart for human brain. Exactly. I mean, there are always going to be questions that we can't answer. Otherwise, we wouldn't have science. So, the Copenhagen interpretation. Essentially, the Copenhagen interpretation. We've already spoken about how quantum particles don't exist in distinctly one state or another until they're measured. So, the idea of the Copenhagen interpretation is that the quantum particle exists in superposition until the point that it's measured, at which point it's forced to choose one of the sort of probabilities.
Yeah.
So that's the sort of state that we observe.
Okay.
So I'm not sure if we properly covered this before, but the different sort of states that I mentioned it. So the different states that a quantum particle or quantum system can be in, they have different probabilities that are applied to them.
Okay.
So that's kind of where quantum tunneling comes into something. So you might have heard of quantum tunneling. So if something has the sort of like a slight probability of, let's say, me in this wall, if all of me has a slight probability of being on the other side of the wall, there is a chance, however small, that I could sort of phase teleport through the wall.
What?
Did you do it? Show me.
No. but obviously that's a minuscule, absolutely minuscule possibility. It's not going to happen.
Is this in the sense that anything is possible?
Kind of, yeah.
Okay.
That's what we were saying. Well, what we were saying earlier about electrons, they've got different. They're kind of more clouds of probability rather than a literal thing orbiting an atom.
Okay.
So it's very. The thing is, it's very, very, very likely, incredibly likely, that we're going to find an electron at this point, at this sort of like distance from the atom.
Yeah.
It's incredibly likely. However, we can't say that we can't say that there is not the chance that it will be in a slightly different position. Essentially, That's kind of what I'm talking about here, that you've got to think of this in terms of probability. And there are things that are very likely and things that are unlikely, but at the point when it's measured, that's when it chooses which sort of possibility it is. I just basically want to clear up here that probability is key here. Things aren't necessarily equally as likely, all of these different states. So yeah. So that's the Copenhagen interpretation. That kind of explains why quantum particles seem to be quite erratic and do what they feel like in ways that don't really make sense to us.
Okay.
Because they exist as sort of basically probability clouds until the point that we measure them, at which point they decide to be a thing.
Wait, so have you explained what the Copenhagen thingy is? Yeah.
Yeah, that's what it.
So that's why I'm confused. Like, what is the Copenhagen?
So the Copenhagen interpretation is the idea that a quantum particle exists in superposition until it's measured, at which point it chooses.
Oh, okay.
That chooses the state that it's going to be in.
So that will become clear, Noah, when Corey finally reveals the other interpretation. When he reveals the other
Many
interpretation,
worlds.
then you'll understand what the difference is.
Okay.
Yeah.
So stick around for that, mister.
Right, it's just all the definitions seem to kind of interlap with each
Overlap.
other.
Yeah.
Yeah,
which,
do,
is,
yes.
It's much like a cloud.
which is why it's confusing when I'm like, are you talking about this or this or this?
Yeah, there's a lot of overlap. But
Yeah.
yeah, basically, if you just hold this in your mind, the Copenhagen interpretation says that things exist in superposition, and when they're measured, they choose.
Okay.
Okay, they choose the one state that they're going to be in. So that's kind of what Schrodinger's cat was made to make fun of, if you understand me. So we're going to talk about
It's
a couple
a parody.
of we're going
Yeah.
to talk about a couple of thought experiments here. And what I love about Schrodinger's cat, one of my favorite things about it, is the fact that people misunderstand it completely. They think that it's sort of a description to show you sort of how quantum mechanics works, and says, "Oh, look how amazing quantum mechanics is." No. He made this up because he said quantum mechanics, it's ridiculous, it's silly, and it shouldn't work. It doesn't match with our sort of normal laws of physics.
Yeah.
And this brings the sort of difficulty of how quantum systems work up to the sort of macro scale that we live in. And it kind of shows how
Ridiculous
it
sounds.
is. Ridiculous
Out
it
of
sounds.
interest,
Yes.
Corey, was Schrodinger, when he came up with the thought experiment, Schrodinger's cat, was he specifically saying that superpositional states and the Copenhagen interpretation was silly, or was he saying that the idea that those quantum states exist on the macro scale is silly, and here's why?
Yeah, it was okay. So it was really to kind of show the problem with the Copenhagen interpretation, not so much to say, "Oh, this is let's scrap all of this." As far as I'm aware, it was more just to say, "Here is a problem with the Copenhagen interpretation," by basically showing that presenting this thought experiment wherein you take the sort of quantum action, how quantum systems work, and you slowly build it up to the point that it's working on a macro scale, and showing how it's basically showing that problem with the Copenhagen interpretation.
Yeah.
Oh,
Does that make sense?
It's fine. It works when things are small and we can't see them. We can absolutely say that this happens, but when it's a cat,
Yeah, exactly. Look, it's like it works so long as your eyes are shut, and as soon as you open
yeah.
But no, okay, so we'll go through the Schrodinger's cat thought experiment. And I need to be very clear. This is a thought experiment. No one has ever done this because that's silly.
Okay.
I
Like
think
the Monty
someone
Hall
must have
problem.
tried.
Someone should try it.
Yeah.
No, we're not.
We could try it on SCI GUYS.
Isn't there a cat in a fridge or something? Was that something you guys talked about, or am I just thinking of that?
I think you're
Cat
just
in a
I
fridge.
think you're
I
just
Don't worry then.
I don't think so.
Okay.
No, so Schrodinger's cat. We start off with a cat, as one might expect. We have the cat inside of a box. The box is sealed. You can't see into the box. It's opaque. All of that. Great. Along with the cat in the box is a vat of poisonous gas, okay, which is connected to a Geiger counter, which is something that measures radioactivity, and also a piece of radioactive material. Okay?
Yes.
All of these things are in the box. Now, there are different things that can happen. Basically, two different things. The radioactive material can decay, and if it decays, it sets off the Geiger counter, which is connected to the poisonous gas, which would then be released,
And then
which would kill the cat.
No more cat.
Nope, dead cat.
Yeah.
Okay? That's one eventuality. Very, very easy. Dead cat. The other eventuality is that the radioactive material doesn't decay, at which point nothing happens, cat lives.
And those are equally likely.
Those are equally likely. So this is the key part here, that the radioactive material, the radioactive decay, works on the quantum scale. And that therefore follows the laws of quantum mechanics. The sort of things we've been talking about beforehand, wherein these things exist in superposition until they're measured. So that means that so long as that gives you basically a measurement system of whether this radioactive material is decayed through using a Geiger counter and a cat.
Yeah, I get where Schrodinger's coming from, because I remember you did like a TikTok video about Schrodinger's cat, and you explained it to me, and I was like, that's so stupid. It's like that's so dumb. It's not science. I won't accept it.
So yeah, that exactly. So then you've got a situation where the box is sealed, so you're not looking in the box, so you've not measured the outcome. Okay, so if you've not measured the outcome, then that means that it's in superposition, which means that the cat is in a position of being both dead because the radioactive material is decayed, releasing the gas, and alive because it hasn't decayed and it hasn't released the gas. It's in both of those positions at the same time. But a cat can't be both dead and alive at the same time. But under the Copenhagen interpretation, this is showing that with the Copenhagen interpretation, that's what we would have to.
It doesn't work
We'd
on
have
a
to
macro
conclude.
scale.
That's what we
Is
have
it
to
both
conclude.
alive and dead?
It's both alive and dead.
Now, what I don't understand there, Corey, is that we have been, one of the things that's a misunderstanding of quantum mechanics a lot is that we talk about measuring a particle's position, for example. And sorry, am I about to ruin?
No. I just knew you were going to bring this up.
Okay. So we talk about measuring, and we think the kind of most people would think that means looking, right? But it doesn't necessarily mean looking. It just means like anything can do the measuring. It means interacting with something, like you say, becoming entangled with another system. And in that case, the other system is the Geiger counter that's measuring the radiation, which that would collapse the wave function.
Yes.
Whether the thing decays or not, the wave function is collapsed by the Geiger counter. Yeah.
So that's the thing here, that there is that issue of which I was gonna bring up next, because it's a really interesting question. That what kind of counts as something being measured or observed as soon as it sort of interacts with something. As soon as it interacts with something else, then it's measured. You know. Well, this is the thing. Some people interpret the Copenhagen interpretation to mean that that means that consciousness dictates reality. In that
there has to be a living
there
thing
needs to be a
viewing
conscious
it.
observer. Yeah, there needs to be a conscious observer for these things to be measured. But obviously, a lot of other people think that
We're not the only things capable of observing things,
or measuring.
Yeah.
Yes.
We are being very selfish.
Well, people are very selfish. Yeah. So there is that issue of, well, it would be the Geiger counter that measured it. But then if it wasn't the Geiger counter that
Also
measured
the
it,
cat.
Yeah, what's the cat saying?
The cat would know if it's alive.
yeah. Again, thought experiment. It's just showing a problem with the Copenhagen interpretation.
Could be going.
What about if the cat? Okay, what about if? Okay, it decays, right? The wave function collapses because of the Geiger counter. The Geiger counter sets off the poison. The poison kills the cat. The cat then can't observe the fact that it's dead, and so the wave function goes back in time, and it doesn't collapse because nothing's observing the closed system anymore, and the cat's alive again.
And observes its dead body. That's it.
No. We forgot about cat ghosts.
What's that scene in Endgame where the rat causes everything to happen?
Oh, the rat did save the day. Yeah,
that's the scene in Endgame where a rat miraculously after 5 years managed to press a button.
Rats don't even live 5 years.
Like, I will tell you,
This rat wasn't alive.
Oh my god, that rat was born after the world was snapped.
Yeah.
Stop.
There's
Amazing.
a flaw.
That rat was less than a year old, which is about the age that rats live in the wild due to predation. But
The fact that Doctor Strange had to view that world and he had to look at that rat save the world, and he was like, "Oh yes, that's the world where things are going to go okay."
How many worlds? Right.
He was looking for the rat. He was like, "Where is it?"
There were what 8 million, 5 million worlds that Doctor Strange looked at.
It was 14 million. I'm pretty
14 million.
sure. Yeah.
Okay, great. How many of those, right, were the rat walking in the exact same place, just a couple centimeters to the right or left?
Nearly, you almost got it.
Is this like in Rick and Morty where Rick destroys his world and then just moves to another reality where he didn't destroy the world?
Yeah, basically it'd be a case of watching all of those very, very similar realities where The exact same thing happens, but just not quite the
It's
right
like
thing.
being edged by a rat.
Another universe where the rat was too skinny to press the button.
This is the thing. I bet you Iron Man didn't actually have to die. Doctor Strange just did not want to watch any more times of that rat having to press the button. He got to one where the rat pressed the button. That was the thing that needed to happen.
This is
That's
such
like-
a podcast. Let's talk about Marvel.
Yeah, we
Okay.
get the pop culture in
It
there.
actually very rarely happens, and I don't really know what's going on. So.
That's
Move
why
on.
it very. That's why it very rarely happens. Because suddenly it's a two-man podcast.
Yes.
I'll just get a cup of tea.
He takes his bathroom breaks. So moving on from Schrodinger's cat, okay, we've got the Schrodinger equation. Now these two aren't necessarily related in that you don't need to be thinking about Schrodinger's cat when we talk about this equation at all. They're just named after the same guy.
Yes.
Okay.
Can you guess who that guy is?
Schrodinger.
Schrodinger.
Well
What's
done.
his first name?
Wow.
Erwin?
Ah,
Oh,
that's nice.
it's a cute name.
Or Erwin? Erwin, I think.
Okay.
Yeah, I think he's Austrian. Something like that. Anyway, it's not relevant.
It's irrelevant. I'm throwing him out.
It doesn't matter. He's gone. Him and his cat too. No, so the Schrodinger equation, it's a linear equation, okay? And that means that, well, with a linear equation, that means that the sum of any two solutions is itself a solution. Now, in terms of the Schrodinger equation, a solution is a state of a quantum system,
Okay.
okay? Because
Okay.
the Schrodinger equation basically can be used to describe the wave function of a quantum system.
Okay.
So
Okay.
basically, with the Schrodinger equation, you've got some starting states. You've got you know some things about the quantum system, and you use the Schrodinger equation to figure out a possible state.
Okay.
And the Schrodinger equation can figure out all of the possible states, thereby giving you the wave function, which is
The sum of all possible
Yes.
states.
exactly.
Ah, yeah.
Yeah, you got it. Nice. We're doing this. So what I'm saying here is, bear in mind, the one good thing to remember here about the Schrodinger equation is that it allows for a sum of solutions or states. And bear in mind that a sum of states is just a superposition.
Yes.
Yeah? Good.
Right.
Yeah? Because it's two states.
So the
That works.
superposition in itself is a solution.
Yes.
Kind of.
Exactly.
Yeah.
So because yeah. Okay.
Yeah.
Good. And in this case, the probability for these different states always adds up basically to 1. Right? So this is just how probability works. Don't worry too much about it. But what I'm saying here is that if you're ever encountering this, the probability will add up to 1. So we can say have one sort of a solution. The probability will always add up to 1. So you've got one at half and the other at half, and they're equally likely. That would be in the
Okay.
case of Schrodinger's cat.
Yeah.
You've got dead cat is
0.5?
half 0.5, and live cat is 0.5.
And that's why it can't be dying, because it has to be 2.
Yes.
Okay.
Well, it's because it's either dead or alive.
Yeah, I never got an answer to that. I've just been thinking about it the whole time.
Well, because okay, the reason that the cat can't be dying is because because then that's kind of like that's a transition state.
Yeah,
which
so
doesn't
it's
exist.
yeah, no, I get
Yeah,
that.
because it's just a thought experiment. We're not dealing with an actual living
Yes.
cat that actually has to take time to die.
Yes.
Yes.
In this
And
case-
dying does just lead to death.
More often than not.
More often than not.
Usually,
Yeah.
I would say. Not
Yeah.
always.
The circle of life.
That is just a
Yeah.
that is a
Yeah.
lie. That is a lie made by the lion dictators to keep the people, well, not the people, the antelope on the bottom. You know, because if they didn't have that lie, the antelope would rise up.
Really
There's
didn't
more in
appreciate
there.
that Disney propaganda.
Uprising.
No.
There's an uprising, yeah, a revolution of sorts. That's the Lion King 4.
Marxist Lion King.
Yeah.
Antelope, the Marxist heroes.
So with this, that can lead to some things having half probability, like in the case of Schrodinger's cat. But we can't measure something that's half a probability. You can't half measure something being there. You know? It's
Yes.
either there or it isn't there.
Yeah.
Yes.
So what I'm saying here is that that doesn't really align with the sort of more macro level of physics that we usually think of.
Yeah.
So on the smaller scale, on the quantum scale, something can be in a superposition, and it can sort of have a probability of less than 1 of being in any different place. But with us, the way that we sort of see the world, things are they're there or they are not there.
Yes.
The probability is 1 or it is 0.
Yeah. I
Yeah.
get that.
What that means is that you've then got one rule for observed systems and another rule for unobserved systems
Yeah.
in quantum mechanics. So if a system in quantum mechanics, like a quantum system, is observed, then it will have to follow the rules that we generally have to follow of, either being there or not.
Yeah.
Whereas if it's unobserved, it follows different rules. It can follow the rules of basically the Schrodinger equation, meaning that it can have multiple different possibilities and be in superposition. Yeah?
Yeah. Don't ask me what I'm thinking. It's not.
Go on. What are you thinking?
No,
multiple
it's just-
different
It's
states.
like the rule for homophobes. It's like I don't mind if it happens behind closed doors. Anything could be happening behind closed doors, but I just don't want to see it. I just don't want to see
you
it.
don't mind if they're in superposition.
Yeah.
Yeah, well, they
You just
could
don't want
exist
to
or they
collapse their
couldn't.
wave function.
Exactly.
It makes sense now.
It does.
Stop shoving it down my throat.
Welcome to my
I
brain.
prefer to be in superposition.
Well, being on top is the superposition. Anyway.
Ooh.
Yeah.
Very nice.
That's actually
No,
probably
it's
being
when you're a
verse,
top
isn't it?
and a bottom.
It's
yeah.
verse, yeah.
Reverse.
Oh, yeah.
You're
very
just
good.
spinning.
Wow. What is your spin? Is it up or down?
Is that little man?
Which type of quark are you?
But bear in mind that means that there's a disconnect. That means that there's a scale where the Schrodinger equation stops working.
Yeah.
And that, if you think about it, Schrodinger's cat, what is that pointing out? That there's a scale where the Schrodinger equation stops working. That there's a scale where the
Cats
sort
are
of
too big.
yes.
No. The point was that cat is the scale. So anything bigger than a cat wouldn't be in
No,
superposition.
okay.
But as long as you're cat, you can be in superposition.
No, that's
You
not-
approach that
don't do-
statement in truth.
You can't say
I believed you for a second.
You can't say things like that with such conviction.
Yeah.
Especially after we started this episode saying Luke could do this without any research. Now you know how it feels to not be allowed to make jokes.
Oh no! I have some authority now.
But yeah, how
Get off! I don't want you.
Okay, so that is kind of a really, really basic crash course on how quantum mechanics works and how we kind of look at it now. Yeah?
Yeah.
So now we get to move on to the interesting part, which is the many worlds interpretation. Essentially what this means, the way that people will usually view this, is that at any sort of quantum crossroads, if you will, when there's one choice or the other, when a particle, a sort of quantum particle or quantum system, doesn't choose to go into one or choose to go into another, the universe just splits into two separate universes. One where the particle does one thing, and another where the particle does another thing.
is this a belief that lots of people have?
That is kind of something that people actually think. So if we talk about it in terms of Schrodinger's cat, just to help you guys understand, the issue with the Copenhagen interpretation is that it means that it chooses one or the other. And also we don't really know how it chooses. Bear in mind.
Like where does that come from?
Like, where does that choice come from? Some people say it's a predetermined thing, which means that, there is no sort of free will. Or some people, it could be any number of, or it could be some kind of thing, could be some sort of value that we're not aware of yet that decides which state it goes into in the Copenhagen interpretation. Now, with the many worlds interpretation, with Schrodinger's cat, it doesn't necessarily, when you open the box, it means that, it doesn't sort of choose one or the other. It chooses both. You will just be in the universe where it chooses whichever one.
So you're just in like the universe
the
where
dead
it decided
universe.
to die.
Yeah.
It just splits into two universes.
Could I choose
Yeah.
to be in the one where it doesn't die? Every single time there's a box.
If you pray hard enough.
I was gonna say that's the fact that you said that was like a predetermined thing. I was like, is this a god thing?
Well, this is the thing. So there are some issues with this, obviously. One of the issues would be where does the energy come from necessarily to produce a whole universe?
To split the universe off.
Yeah.
Yeah.
And why is the universe sort of constantly splitting? What rate is it splitting at? How many sort of universes are there split into? And that's kind of the wrong way of looking at it, as far as I've seen. Now, a lot of this, what I've kind of been reading up on and talking about, I've come from a few different places, but I've primarily taken the takes of sort of two quite prominent physicists. One that sort of agrees with the many worlds interpretation, and one that disagrees. Now, the one that I was sort of listening to the lectures of and things that agreed with the many worlds interpretation had the idea that, okay, we're thinking of the universe as the universe, right? We're thinking of it from our point of view, where we make a choice and then the universe splits off. Now, that is one way of looking at it. But if we think of the universe instead, remember when we were talking about wave functions and how the entire universe is a wave function. and a wave function describes all of the possible states that a quantum system can have.
Yes.
Now, from our point of view, when a sort of quantum system chooses one of those states, that's kind of when it comes into sort of reality for us.
Mhm.
But actually, if you look at it from the point of view of the wave function, those states are all there. In fact, that means that those universes where all those states sort of exist are already there.
So like every possibility is another universe anyway. And it's
Yes.
bound to happen either way. We just don't
Right.
experience that one.
Exactly, we don't experience it, and it doesn't necessarily split off so much as
They're
It's
running
just-
simultaneously and different things happen in each.
yeah, they sort of
kind of-
branch, but it's more of a sort of another
Yeah.
slice of the universal pie. If you look at it from,
You didn't have to say that.
I did written in my notes. If you if you look at it from the perspective of the wave function, it's not necessarily splitting in that sense because it was already sort of a possibility.
Yeah.
There's no sort of energy needed to create an entirely new universe. It's just, oh, crossroads, both of them are existing now.
Yeah, it was already there, but
Yeah.
we're just
So if you think about it this way, so your whole universe is a circle, right? Yeah.
Yes.
Yeah.
Now, a circle is basically kind of like, well, let's say a cylinder is a three-dimensional extension of a circle, right?
Like a tube.
Like a tube.
Arctic roll.
Sure.
Like a loaf of garlic bread.
Right. Well, okay. Now, if your entire universe is just a circle, you can't experience that cylinder, right? But the circles, let's say the circles at different points along the cylinder have a different sort of value of being like sort of 1 away from 0, like 1 away from the end of the cylinder, sort of 3 away from the end of the cylinder, sort of different measurements along the length of the cylinder. Now, from the perspective of someone in a circle, those are completely different and like, unobtainable, and they're if
Yeah.
you're living in a universe
'Cause you
where
can't get to them.
yeah, exactly, you can't
Yeah.
get to them. You're living in a universe where you're at circle 0,
It's like a
right?
tin of Pringles.
Yeah.
Yeah. And each Pringle is
You-
a different.
you live in one
universe is a
Pringle.
Pringle.
Yeah.
That's much easier to understand, I think.
Yeah.
Sure. Yeah. Okay.
Cool.
Thank God you're here.
Thank God. Okay, but from if you pull out, right, and you look at the cylinder, then the cylinder is like the wave function,
Okay.
right? The cylinder can describes all of the circles.
Mm,
The wave function can describe like sort of all of the possibilities.
right.
And when you look at it from that perspective, it's less when you've got different sort of universes being created, it's less sort of popping into existence and more they always had the possibility to exist, and they're kind of when they're given the sort of opportunity to be measured.
We just didn't know which
branch.
slice exactly we were in
Yeah.
until we observed it.
Exactly. And so what this can kind of lead to is, and I want to put a trigger warning here. The trigger warning will be in the description, so we've got some time for you to have a check there in the description. See if
Okay.
you're comfortable with what we're going to be talking about. There are also some, sorry, James, there are some time codes on screen maybe
Yeah.
for when you
Yeah, of
should
course.
click to have this conversation over with.
Don't need to ask me.
Okay, good.
I think
him.
he does. Oh,
Thanks, James. Okay, so that's enough time. Great. So we're going to be talking about something called quantum suicide, right? Or let's call it quantum killing from now on, right?
Okay.
Basically, it's another thought experiment. You've got a man inside of a box, sealed box, same as the Schrodinger's cat box, but without all the other stuff, just a man. Yeah? Just a man in a box.
it's
It's
probably
a
going to
man
have
in
to
a
be a
box.
bigger box, is all I was going to say.
It's bigger than the
Just,
cat box. It's a
don't-
bit bigger.
I didn't say how
Don't
big.
pause and look at me because I will say
smaller man.
something.
It's a box big enough for a man, at least.
A
man.
man-sized box.
Yeah. Not bigger
With
than a
other
coffin.
things also, though.
Bigger than a coffin.
Okay.
Oh yeah, a bit bigger than the coffin. Yeah.
Yeah.
Okay. So you've got a man in a larger than a coffin-sized box. Okay.
Okay.
Yo,
Thank you. You're being so specific.
He's not dead yet.
he has a gun. Okay. And
What the? Someone take this man's gun away.
Yeah. The
With-
box is closed. Sorry.
They could just bury him in the box.
okay, guys, it doesn't matter, right? He's got a gun.
Someone put a lock on this box.
There's a man in a box with a gun, and the gun attached to the gun is a little device that can measure the spin of a quark. Okay,
Yes.
Squin of a pork.
it can measure the skin of a pork like that. Anyway, so it can measure the spin of a quark, and let's say the spin can either be clockwise or anti-clockwise. Now, if the spin is clockwise, the gun cannot fire,
Okay.
and if the spin is anti-clockwise, then the gun can fire.
And both of those are equally likely.
Yes, both of them are
Cool.
equally likely. Yes. Now, given this is a thought experiment wherein, okay, what happens is the man points the gun at himself and he pulls the trigger. The quark spin is clockwise, so the gun doesn't fire. And effectively, this can create a universe. This can create a series. If he keeps on doing that, and the spin is always clockwise, then he can live indefinitely because the bullets are never going to hit him.
He needs to eat.
Right. It's a thought experiment.
Okay, sorry.
He's in a box.
Don't
There's a
think
man
too-
inside a
don't
box.
think too hard on it.
There's a man in a box with a gun and a quark measurer. Like, I don't think that. Like, let's just.
The only options he can do is dead or live.
Yeah, and so basically, continuously, he can pull the trigger, and the gun will not fire so long as the spin is clockwise. Right.
Yeah.
So now he'll live forever. But let's go back to the start again. Right.
Hang on. How will he'll live forever until he just dies of something else?
Yeah. Sure. Okay.
Okay,
Like,
right.
he's
This
not-
is.
don't
I was
think
also
too hard.
confused. I was
like,
also
is this
confused.
some weird hack
It's a
where
quantum.
like
Right.
whoa.
The man has no free will, only dead or live. He doesn't need to eat. He doesn't need to sleep. He has no likes or dislikes. He is just there for the purpose of being killed or not.
He doesn't age.
Stop.
Doesn't do anything.
Let's go back to the start. Okay.
Really?
Yeah.
Okay.
Man in the box with the. Whenever Noah comes onto an episode, right? Whenever Noah comes on, people always say, "Oh, you guys haven't spoken enough about the science. Oh, you're making too many jokes."
What? You look at me. You wait for a response, and I'm already thinking of something,
not
and then you
saying
look
this
at me
is-
until I speak, and then when I speak, I will say what's on my brain.
I'm not saying it's your fault. I prefer the episodes where you come.
Oh,
on.
okay.
I'm just saying that they're not wrong, and I don't.
No, yes.
But let's go back to the start. Okay, man with a gun.
Okay.
The quark spin is anti-clockwise.
Oh.
The gun fires. Man is dead.
Oh no.
Oh no.
So that means literally now you've got a universe where the man is dead, and none of those subsequent universes exist. The many worlds interpretation basically says that those all exist because they're branching off at different points. Whereas the Copenhagen interpretation doesn't really necessarily have a solution for that. It's got like at every point, it will choose one or the other, and then it stops.
Right.
So the Copenhagen
okay.
interpretation,
I get you.
it will become increasingly more likely for the man to die. Whereas with the many worlds interpretation, he will be functionally immortal. Because
Right.
at every it's a 50% chance at every point.
So do people respect the Copenhagen one more than the Many Worlds one? Or is it just...
No. Well, yes and no. These are
Okay.
just thought
A lot of
experiments.
people don't like the Many Worlds one because it fails to pass Occam's razor test, which is basically that your theory should be contain as few assumptions as possible and be as simple as possible. And if your theory is based on okay, let's assume unlimited universes.
Well-
then they see it as a bit wasteful.
This is yes. I mean, that's absolutely right. Occam's razor, the idea that the simplest solution is most likely the correct one, effectively. Which but I'm really glad you brought that up because the sort of argument that the physicist that I was looking into, the argument that they use is the sort of thing that I mentioned earlier. In that, okay, you can say sort of not necessarily infinite universes, but a larger number of universes. If you look at the wave function, there's actually those are already kind of there in existence. Those can be described already.
Yeah.
And so instead of saying that we are creating sort of infinite or multiple universes, we're just experiencing different slices of that wave function. Different interpretations of that wave function are being
Right.
experienced.
Is that in that way you don't need all the energy to make like a million universes more? They already exist.
Yeah.
And we're just living in one or another one.
And what that kind of viewpoint is saying is that, okay, well, we're thinking of this from our perspective, but if we take our perspective to be that of the wave function, then we're not creating a bunch of universes.
They already exist.
They already existed.
Possibilities.
Yes, possibilities. And we, as the beings that we are, can only experience one possibility. That's a
I was going to
limit.
say, wouldn't that say that the universe we currently live in is predetermined 100%? We just haven't seen the future yet?
Well,
Either that or there's some kind of randomness involved,
Yeah.
which Einstein didn't like.
yeah.
Right.
This is the thing. Like, basically, I think the many worlds interpretation is kind of taking the viewpoint of let's take people out of it and look at sort of let's look at outside of our own perspective. Whereas the Copenhagen interpretation does have some limitations, obviously, and the thing is that the Copenhagen interpretation doesn't really solve that measurement problem that we spoke about earlier, that there's one rule for quantum systems and a different rule for everything else. Whereas the many worlds interpretation, depending on, obviously some people disagree with this. There was one person in particular that I saw that had some really great videos, which will be linked in the description, that explained why the many worlds interpretation can't solve the measurement problem. But then also I found someone else that said that it could solve the measurement problem, so I'll explain why they think that can solve the measurement problem here. Basically, what they're saying is that there isn't necessarily one rule for things at the quantum scale and one rule for everything else. With the many worlds interpretation, if you look at it from the point of view of the wave function, then all of those possibilities exist. So the measurement problem is kind of solved in that sense, in that the universe is just kind of split into two, or they both exist, if that makes sense.
How does that solve the measurement problem? As in, like, you don't need to measure it? As in, it's not possible to...
In that, the point of the measurement problem is the sort of, we can't have a probability of half. So when we measure something, we can't have a probability of half. We can only have a probability of one.
It has to be something.
Oh, it's absolutely this or it's absolutely not.
Yeah, it's absolutely this or absolutely not.
Yeah.
With the many universes theorem, the many universes interpretation,
it could be anything.
Well, it absolutely is, and it absolutely isn't, just in different universes.
In different places.
Yeah.
Yeah.
Okay, that makes sense.
So that's how it solves the measurement problem, because like you said, it's basically on our scale things have to be absolute. Quantum scale things can have probability of can exist in probabilities of less than 1.
Yeah. That
And
makes sense.
with the many universes in our scale, it can exist with a probability of less than 1, but it's in a different universe essentially, where that probability is 1. It's complicated. This, like I'm saying, this is difficult, and if you are a quantum physicist listening to this,
help.
I'm so sorry.
well, yes. The thing is that this is not necessarily exactly how quantum physicists will describe it. This is
Simplified.
This is very heavily simplified.
Yes.
And obviously, when you simplify things, you lose some nuance. And quantum mechanics is all about nuance.
Yes.
So it's that's what I'm saying about this episode. Really take it as a sort of jumping off point to look
A
at.
crash course, some might say.
Yeah, exactly. To look at the sort of idea of the many universes interpretation. But what I think is really interesting about this is that it almost takes measurement and observers out of sort of reality.
Yeah.
In that the Copenhagen interpretation kind of can kind of imply that things need to be measured or observed to exist. And some people take that as they need a measurement or a measurer or observer, whereas the many worlds theorem doesn't need that at all.
Yeah.
It just says that all of these things exist already.
Mm-hmm.
And some questions that people often have are, how many universes are there? We don't know. I have no idea. If you agree with this, we don't
Possibly
really know.
infinite. We don't know.
Yeah, it could be an obscene number. We know that it's a lot. So the many worlds interpretation, you've probably got an idea of it now, is essentially the idea that in quantum mechanics, whenever there is the sort of, like I said, the option to go one way or the other, the universe kind of splits. Now, we could get into quantum decoherence and things like that, but that's really more something for another episode, I think. So maybe one day we'll do the Many Worlds 2 Electric Boogaloo. We might have to, because that is kind of...
Well, if it doesn't happen here, it'll happen in another one, so...
Yeah, I mean,
just go to that universe and listen to it.
In another universe, it's probably out by now. But no, that is kind of that's all of the sort of quantum mechanics that I've got for today. I do just want to pose really a question to you guys. Well, one I want to say first, that bear in mind, this isn't fact or proven. This is just a very solid, I say very solid, this is just an idea that some people have of how the universe works.
I'm hearing objective fact.
No, you're not. It's something that has got, as I've said, a lot of problems, and we couldn't cover all of them here today. We've kind of spoken about some of them. There are links in the description. I would genuinely, every week, obviously, I'd recommend reading all of the things we've got in the description. But I've got specifically a few articles that outline some issues with the many worlds interpretation. I've got some things that go in much more depth. There's some really great videos that I found from people that actually have a PhD in physics. So definitely check all that out. And bear in mind, thank you, I just want to say, to my friend Ethan, who helped me out with this episode, who studied some...
Hell yeah.
Thank you, Ethan.
Big ol' thanks,
Smart.
Ethan. Before we start getting wrapped up, I do want to ask you guys a question.
Okay.
At what point are you not you? So let's say the universe splits.
Don't do this.
Okay. All these tiny little incremental changes to your life. At what point are you not you?
They're all me.
Are they all you?
Yeah.
Okay, what about a different sperm?
That's still me.
What about... Really?
Yeah.
Okay. What about... Okay, so let's say a different sperm that changed one gene.
Yeah.
10 genes?
100%.
Right, what if it changed literally every single gene?
Yeah, sure. Why not? There's no answer, Corey.
Are you thinking this through?
No.
No, he's just answering. No, I'm genuine. Like...
Everything me.
When you start thinking about multiple universes, it opens up the sort of the question of what makes you you. You know, you can change one gene, 2 genes, more and more and more. And then at that point, are the kids that you have the same? Their kids and their kids going on to the point where all of these changes, all of these different universes, you've got ones that would be so incredibly similar to the one that you live in that you wouldn't notice the difference. A butterfly flapped its wings somewhere else, sort of thing. At what point would you not become you? I just want you guys to think about it because I think it's an interesting.
These are the kind of
I
thoughts
would
that
elect not to think about it.
I just have no interest in it. I'm like, I don't care. Whatever. Does it matter? I don't
on
exist
me.
anyway.
I may get over it.
Oh yeah, I'll make up for it. I don't know. I'll find something else to think about. I
Okay.
already
All
stopped thinking
possible-
about it. I'm thinking about other things.
All possible future versions of me are me.
Yeah.
But there's only one version of past me that's actually me. 'Cause it's in the past.
Right. I see.
Yeah.
Very interesting.
Yeah.
That's very interesting.
I feel like Luke
I'm
has a
locking
good
in.
answer to this.
But then that means that
No.
This is
You were wrong.
Oh, this is a Luke kind of question.
it is a Luke kind of question, isn't it? Well, what do you think about it, Luke? Where do your thoughts lie?
Well, I mean, it's the same question as if you replace all your cells every 7 years, at what point do you become a new person? It's the same question as if you teleport and all your cells are organized in the same order,
It's
are you the same person?
it's not really the same
I would-
question, though, is it?
Isn't it?
Well, because all of those questions that's more the ship of Theseus. If you replace all the parts, but all the parts are exactly the same, this
Yeah.
is more. Well, all the parts are like how many changes do you need to make to those parts? Like if I was to
Well-
take one cell of your make it a different cell, make it. A different
I mean, my
cell.
answer would be that I don't personally consider and identify myself as being the physical matter in my body necessarily. I consider myself to be the stream of consciousness. So it doesn't matter what you do to my physical matter. It doesn't matter if you change my genes. It doesn't matter if I was a different sperm. What matters is where my stream of consciousness ended up and why it ended up there. So I don't identify with the question.
No, but seriously, that is the many worlds interpretation. At least, a kind of intro to it. And you shouldn't walk away from this thinking this is exactly how the universe works. What I would really like for you to walk away from this is maybe a slightly deeper understanding of some interpretation of the universe and the kind of drive to find out more.
Meant to
using
get the
all
juices
links.
flowing, you know?
Yeah, exactly. Get those
Yeah.
juices flowing. Get them flowing into the description where I've got all the links that you can click on.
And to our Patreon, patreon.com/SCI GUYS.
Yes, because thank you very much. That's our patrons that voted for this episode. And I've just realized we need to read out our patrons by the end of this episode.
Oh, holy shit.
It's another thing you get if you're a patron. So why don't we start reading out the patrons about now? Luke, would you like to start?
Thank you very much to JP.
Okay, that's fine.
Rachel,
Thank you very much to Rachel. Thank you, Rachel.
Thank you very much to Violent Orchid.
Thank you, May or My.
Thank you to Spider-Man himself, Peter Parker.
Oh,
Oh, wow.
thank you, Abigail Pierce.
Thanks, Olivia.
Thank you to Abby.
Thank you to Moni Berg.
Thanks, Elizabeth Robinson.
Oh,
Thank you to Harry Routledge.
Thank you to Evan Beige. Evan. Thank you, Evan.
Thank you, Kaylee Teagan.
And that's it.
That's it. That's everyone this week. Woo! We're
It
doing
was
it
a
a little
lot
bit
shorter
early.
than last month.
We're doing it a lot earlier than
We need
last
to try
month.
We
harder.
did it. Oh, that's it. We're
Last
doing
month
it
we
earlier.
waited to the end of the month.
yeah.
This
These
month I
are-
thought
New patrons?
these are new patrons.
Yeah.
Yeah, all these
Crazy,
patrons have
right?
joined up since the last time. And if you want to have your name read out, you can go ahead and sign up to patreon.com/SCI GUYS. Have I said it enough? I think once more.
Yeah.
Maybe once more.
Once more.
Yeah.
Patreon.com/SCI GUYS.
Well done, Luke. Thank you very
mate.
much.
Luke would like to leave. He's very bored now.
Thank you for watching. You can find the full references for this episode in the description. Subscribe for new episodes every Sunday, and why not leave us a nice wee review? You can support the pod at patreon.com/SCI GUYS or find and contact us at SciGuysPod on Twitter, Facebook, and Instagram, and now TikTok too. You can also send us an email at sciguyspod@gmail.com. I am not Corey everywhere.
I'm Jamkin everywhere.
I'm Luke Cupforth everywhere.
I'm NoahFinnce in some places and NoahFinn Adams on Twitter.
Goodbye.
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 Bye.